In this clip, we will cover how to use multimeters to make key measurements related to an electrical system. Specifically, we will look at how we make measurements of voltage, current, and resistance, and how we use this information to ascertain power. As you may recall, voltage is the measure of electric potential. This potential needs to be relative to some reference. As such, when we measure voltage, we are conducting the measurement between two distinct points. If we are interested in the voltage drop across an element, as we see here, then we must place the multimeter in parallel with the element. And we denote the circle with a V as our voltmeter. Clearly, by placing the multimeter, or in this case the voltmeter, in the circuit, we have provided another path for current to flow. So what characteristic do we need the multimeter to have so that it doesn't impact the measurement and the rest of the circuit? By the current divider rule, to avoid current flow through the meter, it must have a very large internal resistance. Ideally, it should look like an open circuit. For AC circuits, your voltage measurement will be the RMS voltage, and that's always positive. However, for DC circuits, you need to ensure your negative lead is located at your reference point. Your multimeter will have a red and black lead, and by convention, the latter, that is the black, will be your reference. In our voltage measurement example, we are looking at the voltage dropped in a divider circuit consisting of a 3K ohm and a 1K ohm resistor placed in series. Specifically, we are measuring the voltage drop across the 1K ohm resistor. From the voltage divider rule, 25% of the total voltage should be dropped across this element. This is verified on the multimeter that is reading approximately 0.4 volts, that is 25% of the 1.6 volt voltage source. As this is a DC circuit, if the red and black leads were reversed in the measurement value would have been negative 0.4 volts. Current is the measure of electron flow in our circuit. As such, to conduct current measurements, we place our instrumentation in series with the element of interest. So here's our element, and we will place our multimeter, in this case configured as an ammeter, in series. As we just saw, series elements will drop voltages according to the voltage divider rule. So we'll see some voltage drop across each of these elements due to the current flow. If we are to ensure our instrument does not impact our measurement, then we need to have minimal voltage drop across the meter itself. As such, our ammeter should have very low resistance. Ideally, it should appear as a short. As with voltage measurements, the lead configuration is important when doing current measurements if we have a DC circuit. For our current measurement example, we again consider the series circuit consisting of a 1.6 volt AA battery, a 3K ohm resistor, and a 1K ohm resistor. We see that the instrument is placed in series between the battery source and the 3K ohm resistor. We also note that the leads have moved to a different set of jacks on the multimeter. As noted, the internal resistance of an instrument must be very low for current measurements, and thus many multimeters have distinct circuitry for current measurements. So do check to make sure your leads are located properly for the measurement you are making. Here we see our measured value is approximately 0.4 milliamps, which is 1.6 volts divided by 4 kiloohms, and thus in agreement with Ohm's law. Our next measurement is that of ascertaining the resistance of an element. Generally, resistance is a property of the element itself and not a function of its placement in the circuit. As such, when we make resistance measurements, we ensure that the element of interest is disconnected from the circuit as much as feasibly possible. This includes ensuring your circuit is not powered while you're making the measurement. We measure the resistance across an element by placing the meter in parallel. here's our element, and we'll place our meter in parallel, and we're measuring resistance. The multimeter is applying a small voltage and measuring the resulting current. There's current, and there's our small voltage. And by Ohm's law, we get the resistance value. In our example, we are measuring the resistance of the 1 k ohm resistor. That, as we see, is resulting in a measurement of 0.9892 kiloohms, or 989.2 ohms. Note that we have disconnected the battery lead from the circuit and thus isolated the resistor from the rest of the circuit. This particular resistor has a tolerance of 5%, or 50 ohms, and we see our measurement is well within that range. We note for this multimeter, we simply select ohms for the resistance measurement, and the instrument auto-scaled to the right range. When making your measurements, ensure your instrument adjusts to the right scale, or if that functionality is not available, that you manually set the scale appropriately. In this example, we are measuring the resistance of a 2.2 k ohm resistor. In the left image, the scale is set to 2 mega ohms, and the reading is 0.002 mega ohms, with no additional digits. On the right, a 20 kilo ohm scale is selected, and we now read 2.13 kilo ohms, a much more useful and accurate reading. The focus of this module is power measurement, so is that something we can do directly? The answer is yes and no. We have an instrument called a wattmeter, but that is effectively an ammeter in series and a voltmeter in parallel with the element of interest. So here's our element. Our ammeter would be in series, and our voltmeter is in parallel. We then determine power by the product of these two measures. Here we have our example in which we are now looking for the power dissipated by the 1 kilo ohm resistor. The left meter is measuring current through the complete circuit, and we can see that the reading is approximately 0.4 milliamps. The right meter is measuring the voltage across the 1 kilo ohm resistor through these leads, and we see that the reading is approximately 0.4 volts. The resulting dissipated power is approximately 0.16 milliwatts. Note that these current and voltage readings are similar to what we measured individually for the currents and voltages. Thus, we verify that the instruments themselves have little impact on the measurements being made due to the large internal resistance of the voltmeter and the small internal resistance of the ammeter. From our last example, it is clear that putting an ammeter in series and a voltmeter in parallel is a cumbersome approach to ascertaining power. So what might we do in practice to make things more convenient? Well, for AC systems, we can leverage concepts that you may have already covered in regards to transformers. These ideas will be addressed in the next part of this module.